First of all, we define vorticity as a curve of the velocity. And we define a solution of the incompressible Euler equation, which describes a single vortex. So if the vortex is located at 0, then the streamlines the direction of velocity at this point velocity like that. And analytically, it is kappa is the strength of the vortex, and we actually have to multiply by anti-symmetric tensor. Now, clearly, the vorticity is the velocity of an induced by a single vortex is orthogonal to the radius vector, namely, and because of that, actually, you can we know that vorticity satisfies the equation. Which we will actually generalize today. And if you imagine, for example, vorticity to be a function of x squared, spherical symmetric, it's located at some point, but we can smear this point a little bit in a symmetric way. Then the derivative will be proportional to the radius vector, while the velocity is orthogonal to it. So it is completely consistent. What follows from it is simply the statement that it would be inconsistent to have kappa to depend on time. So kappa is a constant, as we said. And this is a rather trivial consequence of the equation, kappa dot is 0. We will see that there are, in multidimensional case, there is an interesting generalization of this type of statement, but that's a rather minor result. What was much more interesting is to look at the equation, at this equation, then for this particular case, omega is equal to kappa delta function of x. But it's interesting to consider a collection of these vortices. Those vortices, they live their own life, actually. And this life is quite interesting. They move in a strange way, as we saw. We will try to understand it today. So in any case, this is the velocity induced by a collection of vortices is simply a superposition. We simply say, let's take V alpha to be 1 over 2 pi epsilon alpha beta. And we can write it down, for example, as in several ways. One way of writing it down would be just to take x beta minus xa beta, x minus xa square, and put the sum over a and multiply it by kappa a. So this is just the velocity produced by, at some point, by the collection of vortices. And we can also write down, another useful way to write it down would be epsilon alpha beta, sum over a, or I would put it where the function f is sum of the logarithms of x minus xa multiplied by kappa a. Or shall I call it? I think I call it phi. This is not an equation yet. This is just the statement that velocity field is given by this formula. And here in this formula, you can actually think of xa to be constant, or we don't know how it changes. And what we discussed last time was that when you plug it into this equation, the result is very simple and intuitive. Namely, the equation is simply that the vortex number A, the velocity of the vortex number A, is equal to the velocity generated by all other vortices except this one. The vortex doesn't act on itself. That we see from this equation. That single vortex doesn't push itself. It's symmetric, and so kappa is a constant. It stays at rest. But other vortices, they do push their neighbors. So it's probably should be. I should stress that we should not include here the vortex itself. So the equation, final equation, was that it's kappa A, kappa B divided by 2 pi, epsilon alpha beta, xa beta minus xa alpha, xa minus xb square. And important, there is of course a singularity, then b is equal to a, but we avoid it. As we learned, there is no influence, self-interaction of the vortex. And this is the equation. And I actually gave you an exercise last time to spell the name of Kirchhoff. Who knows how to do this? Yes? C-H-N?
O-F-F.
Almost, but believe it or not, it is double H, and it is double F. That's, I'm not giving you trivial problems. Anyway, this is the Kirchhoff equation, and we saw, we will transform it a little bit and see how it can be used. First of all, it's very convenient. Well, there are many things to be understood here. First of all, as with any dynamical system, the first question you try to ask is whether it belongs to the well-known class of systems like Hamiltonian systems. As we said many times, when we have Hamiltonian system, it means that you have several objects in your hands. First, you have a phase space. You define some even-dimensional phase space. Then, which in some simple mechanical system is just collection of momenta and coordinates. So if you have n particles, you have n momenta and n coordinates, and together they form a phase space. But generally, the phase space does not split naturally onto momenta and coordinates, but it's just even-dimensional space. Then on this space, you should be able to define either it's more or less the same thing, either the Poisson brackets, so, or the symplectic form. And you should be able to define a Hamiltonian, which is, the Hamiltonian is just a function on the phase space. So we have to decide, the first question we have to answer is whether this is a Hamiltonian system or not. So what would be, and let me also write it down in a more suggestive way. I shall write it down as, I think I shall write it down in this way. You have kappa A, x A alpha dot. This is the rare case when we don't sum over A. A is a particular number, and it is equal to epsilon alpha beta where F is sum over A not equal to B, kappa A, kappa B divided by 2 pi, logarithm xa minus xb square. So when you actually differentiate, you get precisely this expression. If you differentiate the logarithm, and kappa A will simply cancel in the left-hand side and in the right-hand side. So it's just a useful identity, useful way to write this thing. And the first question I would like to ask you, what it reminds you of. It's similar to something which should be familiar, this type of expression. Anything? Think of various physics problems which you know. Oh, for example, if you have electric charges in space, in three-dimensional space, what would be the potential energy?
Proportional to 1 over r, or a sum of 1 over r terms.
Yes. So what's the difference with this guy?
That's the derivative, or the antiderivative of 1 over r.
Well, actually, first of all, in three-dimensional space, we would have, instead of the logarithm, we would have 1 over xa minus xb, right? Okay. So if this distance was in denominator, that would be simply the Coulomb energy of electric charges. But, okay, now try to remember some comments which I made last time and interpret this in the same spirit, this expression with logarithm. What is with in 3D we had 1 over r. By the way, what was 1 over r? What is the mathematical property of 1 over r, which was responsible for its appearance in the Coulomb energy? Why it is 1 over r, in other words? Yes?
I think it's the delta function, is that?
Yes. Actually, it's because, that's right, we have the Poisson equation for electrostatic potential, and when we have a single charge, we have some 4 pi or something, multiplied by the delta function, and phi from this, what I did last time was dimensional analysis. Phi, this scales like 1 over x squared, this scales like 1 over x cubed, and we get the phi 1 over r. Same logic in gravitational case. It's both electrostatic potential in the Coulomb law and the Newton potential in gravity. Okay. Now, in 2 dimensions, I mentioned it, the solution of this equation in 2 dimensions should be scale invariant, and in fact, it is logarithm of x. If you have two-dimensional charges, their Coulomb energy, it's their Coulomb energy. By the way, how to understand it physically from the point of view of three dimensions? Just think how to genetically connect 3D and 2D. What would I claim that in 3D you also, in certain configuration, you also have this expression with the logarithm, which is the 2D answer. How to visualize it? So this is the interaction from the 3D point of view. This is the interaction energy of two-point charges, right? Separated by distance r. And what is, from the 3D point of view, the logarithm of r? How would you? It's also some electrostatic configuration. Imagine the lines, the kind of strings perpendicular to the blackboard. And these strings are charged. If you integrate, if you look at the interaction, so it's basically electrostatic interaction of two wires. And it is the same as two-dimensional point-like charges. You can just take a perpendicular plane, and these strings or wires, they cross it at certain points. And the electrostatic energy, as you can check yourself, will be the logarithm. For the same reason that the solution of the Laplace equation is in 2D is logarithmic. And if the lines are infinite, the energy doesn't depend on their length, on the position in perpendicular direction. Okay, that's not terribly important comment, but just I wanted to just to give you some perspective. All right, so that we rewrote this, and this looks like a Coulomb energy of point like two-dimensional charges. It is actually a point, electrostatic energy. However, we noticed last time that by taking simple examples, that these vortices move completely differently. They move differently from charges. Remember, we had the picture when, if you have the vortices which are rotated with the same charge, they will move. With the opposite charge, they will rotate around each other. Very different to what we have in the case of electric charges, when simply same charges repel, opposite charges attract, and that's it. So we can try to compare the equations which we have. Yes?
When you have electric charges, when you move them around, you usually have like some propagation, right? So
I assume we are dealing with electrostatics, so you move it very, very slowly, so not to generate electromagnetic waves. Of course, if in reality you...
Yeah, but in this equation, can you get sound waves when you move the vortices?
It's no, it's purely static equation. It does not, in this approximation, it's electrostatic approximation. There is actually, I'm slightly ahead of myself, but there is a quite wonderful theory. All these vortices, they appear not only in nature, in the form of tornadoes, etc. We will be discussing 3D, but they also appear in superconductors, and in superfluid helium, and in these cases they are quantized. Those vorticities are integers. Now, it turns out that they form a lattice in superconductors, and this lattice, this lattice can oscillate, and there are excitations of the lattice, kind of sound, which is just fluctuation of this collective motion of these vortices. So it's quite interesting that, first of all, the vortices themselves are not really, they were not really present in the original system. They are the result of collective motion of the original system, and then the collective motion of the vortices themselves generates sound. So there is such thing. Actually, I will give you today an example. Again, we will see what happens if you have a body in the fluid moving. In the wake of this motion, you will have a vortex. We will see that there is a vortex lattice, and there is some regular, but there is no sound in this approximation. There is no sound here because, in particular, because we assume that the fluid is incompressible, and that. Okay, but I'm running ahead of myself. We now have to understand what's going on. So what's the difference between the equation of motion for electric charges and for the vortices? The potential energies turns out to be the same. But how would you write down the corresponding equation for the electric charges? What will replace this equation? So you have just, it's not a difficult question at all. You just have remember the general principles. It's not. So my question is, you have a collection of electric charges, pluses, minuses of various values, and so on. We already know that their potential energy is this. How to write down, when you know the potential energy, how to write down the equation of motion? So it's kind of a trivial question.
Yes, so just negative ddx. Of the negative d potential.
Yes, but okay, but that's what we basically have here. But what about the left-hand side? In case of charge, the left-hand side is here. It is for vortices. What it would be for charges?
The second derivative.
Yeah, it will be second derivative. So it will be a different equation, and then we will find in a few moments, we will find the system which interpolates between electric charges and vortices. But before I do this, I want you to figure out. So, by the way, what would be in the case of electric charges? What would be the Hamiltonian? What would be the phase space? It's obvious that electric charges is a Hamiltonian system. So what is the Hamiltonian, what is the phase space, and so on?
So are we talking about electrostatics still?
Yeah.
So they're unmoving. So then the Hamiltonian is just potential.
Oh, well, but the charges can move. Okay, you take the potential, this kind, but then you have to write down the condition for equilibrium, right, of these charges. What would be the condition for if you assume they are not moving? So what is the condition for the equilibrium?
Yeah. Yes, so the sum of all the d potential dx is 0.
Yeah, actually that all partial derivatives with respect to xa should be 0. And there is a well-known electrostatic, people were looking for this in the end of 19th century because they wanted to build the theory of atom and they didn't know quantum principles. And there was a no-go theorem which says that when you have electric charges only, there is no stable equilibrium there. But in any case, anyway, it's all correct. So what is in the Hamiltonian? So the charges do move, and it's just like with any particles. For the charges, you have coordinates, you have momenta. So you have the usual phase space, and the Hamiltonian is the sum of the potential energy and kinetic energy of the moving particles. When I'm saying we're doing electrostatics, by the way, it means that we neglect radiation which comes from the particles, and when it is legitimate for the system of charges. What do you think is the criterion to make it
So the particles are moving much slower than the speed of radiation?
Yes, which is usually called speed of light. Okay, yeah, right. In any case, here we have something different. And what I want you to do is to try to define the phase space. And I can tell you in advance that the system is Hamiltonian. But you try to figure out what is the Hamiltonian and what is the phase space. What would be natural. Remember, we have the general principle, I remind you, Hamiltonian systems. We have the phase space, which is even dimensional, and we have the Poisson brackets, which is supposed to satisfy the Jacobi identity. That's the condition on the possible Poisson structure. And the equation of motion are just the brackets of the Hamiltonian with y, which gives us E alpha beta of y dh dy beta, where E here is, as I said, is some antisymmetric matrix of the size n by n. And, that's the Hamiltonian equations of motion, and they will be Hamiltonian equations of motion with all the nice properties like conservation laws, etc., Liouville theorem, provided that E is that y alpha, y beta, y gamma plus cycles is 0. So that's the general stuff which I wanted to remind. I think I want you to remember it very well. You can also, what we call the symplectic structure, which enters the Lagrangian, actually, is the inverse. It's the inverse of this matrix. And you can, of course, write it. It's just the same thing. Okay, returning to our concrete example, try to think of what is the phase space? What would be the nature of phase space, and what would be the nature of Poisson brackets? Just always try to see similarities between completely different formulas. So I just reminded you about this Hamiltonian system. You see that even graphically it looks very, very much similar. So you have just to
So the top equation seems identical to the equations of
yes. Actually, the answer is very, very simple. The answer is that you, first of all, first, the most important part is that the phase space here is simply the coordinates of the, if you have a single vortex, it has coordinates x1 and x2. And so the phase space here consists of coordinates of those xi alpha. There is no, very much unlike the electric charges, there is no x and p here. The whole phase space coincides with the configuration space, and that's quite unusual. And it is clearly doesn't make, of course you can declare that, say, x component of the coordinate is a coordinate and y component is a momentum. You can say this, but it doesn't make much sense. It's totally arbitrary and breaks down symmetry. The right way to interpret it is simply to say that coordinate space coincide with the phase space in this case.
Excuse me, so
yes.
in odd-dimensional cases, there's no Hamiltonian structure?
Well, in odd-dimensional cases, it's tricky. It's usually, if you take it literally, you have a the problem with odd-dimensional spaces is that you have some degeneracy, but you always can remove, there are some artificial tricks to remove this degeneracy and effectively reduce it to two-dimensional space. For example, when we have the one example with the unit vector, well, I will not go into this, I think. But generally, typically, yes, you need even dimensional space. If you have odd dimensional space and you want to very much to impose the Hamiltonian structure, there are some tricks to do this, like excluding some coordinates and so on. But that will take me too far to discuss now. So all we have to do is just to declare this potential energy as a Hamiltonian. It's not now, it's not a part of the Hamiltonian, it is a Hamiltonian. Okay? And if I take xi alpha, xp beta, then the brackets for different guys, of course, are the same. Are 0, you have kappa A minus 1 to take into account this kappa A, and you have epsilon alpha beta, which is just 1 and 0, is 1 and or minus 1. Epsilon alpha beta is numerical tensor. And the phase volume in this case will be simply the area occupied by vortices. Now, one more thing, we still don't understand its relation to electric charges, and I want you to, and we don't, well, this funny way these things move is related actually when the equation of motion contain epsilon tensor. um, it means always like a dozen, some kind of gyroscopes, and also it means a very, very strange way the system moves. Like here, instead of repelling or attracting, it rotates or moves and so on. It's a little bit like if you have a bicycle wheel, you rotate it and you push down, it actually moves in different direction. So there's always epsilon tensor means some funny way of motion. But we don't understand how it's related to electric charge. And one last thing I need, one thing I need here is the Lagrangian. Let's write down the Lagrangian. In the Hamiltonian system, remember, the action was where A was the potential which gave us the curl of A was the symplectic form. That was what we derived. And so we have to figure out what this term will be in our case. As a matter of fact, by the way, another way to understand it, we postulate the Hamiltonian system. We said that the system is Hamiltonian if we can write down the equation of motion of the first order in derivative, so that only initial data are needed. We don't need, and it's this phase space is the space of this initial data, which is y alpha at 0. And here we already have the first order equation of motion. That's why. But it's a small miracle that it's a Hamiltonian system. But, all right. So how shall I write the action for these moving guys? Well, I would write, well, maybe you suggest some natural expression for the action. The action, of course, will contain this term, which is f is now the Hamiltonian. And so y's are now x. The only question is, what is this term?
Is it kappa sub A?
Is what?
Is it kappa sub A?
It's well, yeah, it's kappa sub A, of course, but it also has epsilon alpha beta. Now, if you vary this guy, remember we had this example. If we vary this guy, we will get precisely this equation. So the equation is follow from the variational principle. And now imagine imagine a particle with let's concentrate on the particle number A. So we have this expression. Let's consider this particular action. Because I want to understand what this term means, and the action for electric charge would be. By the way, what would be the action? This is the action for the vortex. And for the electric charge, what would be, maybe I should not write it separately, just let's look at this thing. So what would be the action for the electric charge? So let's write the action for electric charges. The thing which will stay the same is H, which will be potential energy. So what should you add here?
mv squared.
Yes, it's simply ma xa dot square divided by 2 minus h. Yes.
In the electric case, doesn't H contain a m over 2x dot squared?
No, by h, I probably should use a different letter. Let's call it F. So in electric case, F is potential energy. In vortex case, it is full energy. So it's a full Hamiltonian. So this is for vortices, this is the conserved quantity. Then they move. This Hamiltonian remains constant. But for electric charges, potential energy changes. You have kinetic energy. So you have a difference between kinetic energy and potential energy. Okay? F is a potential energy. And now let's combine these two things. And let's suppose that both terms are present. And let's try to understand the action which interpolates between electric and hydrodynamic thing. Let's write it down, and we have this thing. And I want you to interpret physically what is going on. What kind of system it describes. Without it, it describes simply electrostatics of charges. But what is this term from the electromagnetic point of view? If this term, notice the following thing. I will give you some hint.
Is it some sort of angular momentum?
Yeah, it is angular momentum term. It is correct to say this, but it doesn't clarify. I wanted to formulate it in more physical terms. Yes, it is angular momentum. Now, if I write down the Newton equation, I will get, by varying this thing, kappa A, epsilon alpha beta, x A beta dot, minus df okay, so we have this term is just electrostatic force which act on the charge, this gradient of this guy. But what is this term? What kind of it is some strange force which we have here, which contains epsilon tensor and therefore actually moves in an unexpected direction. Yes?
Is it magnetic force?
Yeah, it is magnetic force. Actually, what I'm driving at is that this is a system of electric charges in perpendicular which move on the plane of the blackboard, and they are they are placed in a perpendicular magnetic field. You have magnetic field perpendicular to the blackboard. And what is the name of this force in physics? It's the Lorentz force, yes. And the reason why this Lorentz force is, there's a general reason why it doesn't contribute to the Hamiltonian. Why it is not, if we drop this kinetic term, then the Lorentz force is always, the general expression for the Lorentz force is a cross product. And it's always perpendicular to direction of motion, so it doesn't perform any work. And so that's the reason why without this term, that was a full Hamiltonian of these particles.
And so it's also total time derivative, that term you added?
Sorry?
Oh, never mind. Yeah, no, it's fine.
So what I'm saying is that we now can, in principle, can go from the limit when magnetic field is negligible, which means very large M. If M is very large, then you can drop this term. If kappa is very large or M is small, you can drop this term. And so you get the motion of vortices from this, if you want to, from this Hamiltonian by taking large term here. And this explains why the vortices move so strangely. It's because in magnetic field, electric charges tend to rotate. And when you have their interaction, these rotations superimpose on each other and so on. But the essence of this strange behavior is this epsilon tensor, just as it is the strange behavior of the gyroscope, where you push the gyroscope in one direction, but it moves in a perpendicular direction. That's because of the mathematically, it all sits in the epsilon tensor. But this is the epsilon tensor with 3 indices in the case of gyroscope. Okay, now one more thing, and we will move to 3 dimensions. It's very convenient to write down to discuss the motion of vortices using complex variables. Actually, always when you have 2 dimensions, complex variables is a good idea. Complex analysis. Well, this we can always write down, introduce the complex velocity. It will be convenient for me for the future consideration to put a minus here. We define the complex velocity. And this complex, let's compare it with our vector notations. You see that V1 is kappa divided by 2 pi x2. V2 is minus kappa divided by 2 pi x1. Now let's form the complex velocity. It will be kappa divided by 2 pi, and it will be x2 plus I x1 square plus x2 square, and it will be simply I kappa divided by 2 pi 1 over z, where z is x1 plus ix2. You see I'm taking I out, so you get x1 minus ix2, and you have this nice formula. And when we now start looking at this equation, we will get the following in complex coordinate. So we are simply rewriting this by introducing complex variables, and the answer will be, if you do this, z bar I dot is equal to I You see, it's much simpler form much nicer in complex variable, because we can really divide it, have this complex analysis. It's very easy to understand why there are a few things to be understood here. So this is the complex form of the Kirchhoff equation. First of all, let's understand why it appears to have z bar here and z here. It's related to symmetry. Have you any idea why? And it's, of course, if you do the algebra correctly, you will get this result. But why? What it means from the symmetry point of view? I can give you a hint. Think of rotation symmetry of the equation. How this left-hand side and right-hand side transform. How to explore the rotational symmetry of this equation. What you're supposed to do.
So, I mean, I guess we're going to replace z with e to the I phi.
Exactly.
And then...
And then you see you get e to the minus I theta here, and also e to the minus I theta here. If you write down z instead of z bar, you break symmetry. It's so that's one small point. The other small point is it's a more physical puzzle. We derived it from the Euler equations, which have been Galilean symmetric, and it's one more mini puzzle with Galilean symmetry. But it's clear that well, how would you try to see what the Galilean symmetry would mean in this equation? Let's try to check if it is present in this Kirchhoff equation. So what should you do for Galileo?
I guess z dot you would add a constant, and on the other side you would have a plus vt that would cancel.
Say it again?
So on the left-hand side you add a constant.
Yes.
And on the right-hand side, the velocity term cancels.
Yeah, that's right. So there's no symmetry. There is a symmetry under translation. So if you simply make that and translate it to A, to C, then this term will cancel here, cancel here. But now if you try to add Vt here, then we get So we don't get Galilean symmetry here because it coincides with the statement which we made last time that two vortices, they move with particular velocity. You cannot really choose it arbitrarily. The difference, by the way, with this equation, if we don't have this thing, then indeed the adding vt, when you have second derivative, you have Galileo. So try to think at what moment we lost Galilean symmetry here. We did the derivation, and that's very typical for the work in theoretical physics. You come up with some contradictory result. You started here with Galilean symmetry, you end up without symmetry, and it's usually very instructive to backtrack and see at what point you lost this symmetry and what it means. And I shall give you a hint also that the symmetry was lost already at the level of a single vortex, which we claim is the solution of this equation. When you look at this expression, which solves the Navier-Stokes equation, then what can you say? Well, what can you say is that at infinity, it assumes that this is indeed a solution, but there was an implicit assumption that at infinity, velocity is zero. So the frame is already chosen. It's the frame which has zero velocity at infinity. And otherwise, to go to a different frame, you have to rewrite this expression for the velocity. In the moving frame, it will be also a solution of Navier-Stokes, but it will be different solution because you get a constant here. So that's kind of interesting. Now,
Sorry,
yes.
Could you remind me again where the top equation comes from?
Oh, this one?
Mm-hmm.
Okay, it was just the chain of argument was this. We have a vector. Excuse me. We have the equation. And we found the solution of it is, which is epsilon alpha beta x beta divided by x squared. Omega is here epsilon alpha beta d alpha v beta. It's a curl of v. So it's a concrete equation and it's a concrete solution. And this is the same solution written in complex variables, which is not needed for the argument about Galileo. It's completely irrelevant. Complex variables or real variables. What is important is that when solution is derived, we assume that velocity tends to zero at infinity, and it does. And that selects the frame, the particular frame in which the equations are supposed to be true. In different frame, you have different equations. That was precisely the situation, by the way, with the Maxwell equations before Einstein and Lorentz. People noticed that if you have, in some frame, you have the Maxwell equations describing, say, the light wave, then when you go to Galilean, to a different frame, and use the formula of Galilean transformation, Maxwell equations will change. So in different frames, we will have different equations. And Einstein said that it should not be so, that let's postulate that the equations are the same in all frames. That's the relativity principle. And then you immediately derive, you you have to change from Galilean transformation to Lorentz transformation. But here in hydrodynamics, so it was a non-trivial assumption. It doesn't follow from anything except for the experiment that it's not logical necessity that the Maxwell equations, well, you just write down the equations, you make the substitution, the equation changes, like they do here. And maybe that's, for some equations like this one, that's the correct answer. It's not a logical contradiction, but for the Maxwell equation, then Einstein postulated that the equations should not change, and then the whole majestic picture of relativity arises. But you should remember that it's a conjecture which was justified by experiment. It's not a logical necessity. Okay. So we'll have in homework a couple of exercises for this. It's a lot of fun to study this equation. I'll tell you one important case in which this equation are used. As I said at the beginning of the class, if you have a motion of a cylinder in the fluid, then you can show that that behind the cylinder, if the speed of motion is not too large, if it is very large, then this is a turbulent wake behind it. But if it is not too large, there are beautiful photographs. There is a vortex. It's called the vortex street, or Karman. Which was noticed by Karman. And the whole thing of these vortices, they are arranged in such a way that they are regular and they move, they follow the body. As we saw when you have, when we have the thing like that, well, it's actually should be, if the body moves like that, it should be this way. Then this system of vortices, you can show it from this equation, which is quite simple, but I don't have time for this. It's quite simple to see. There's one simple thing which I simply don't have time, but there's also a highly non-trivial thing for which the analysis is not complete. You see, there are two solutions of this equation, and that's you may try to find them themselves. Both solutions are moving behind the body. One is this triangular lattice, and the other is simply square lattice. They both solve this equation. They both move behind the body. Experimentally, however, you always observe this thing. And theoretically, how it could be possible. So what else? Suppose we found the solution of this equation, and we found two solutions. And as I said, it's a very simple step to find the solution of these two equations. What the complicated step is to decide why one solution is right and the other is not. Can you think of some principle which would select the solution? Think about what can happen in principle for when you have the motion, which solves the That's quite important, which solves the equation of motion. But sometimes it may not be physical. Because of what? Well, remember, for example, it's when you look at the Euler equation, when I gave you this example, you have, say, water and air, and water is at rest, and air moves like that with some velocity. And this is a solution of the Euler equation with these two different velocities. However, this solution does not survive. Why? What happens?
Stable?
Yeah, exactly. That's the point. That's the point here, and I will explain why. Actually, here it's very simple to explain why it's unstable under small perturbations. It's just as we also looked at gravitational stability. So, how people did this stability analysis, which is the following: you take this structure, you change ZA to ZA plus delta ZA. And turns out that for this case, there are exponentially growing solutions, while for this case, they are not. That's complicated numerical analysis, actually. It's not a... it's very easy to write down this equation, but to analyze them, it takes a lot of effort. So it's just a beautiful thing. And another multiple applications of vortices are in the theory of superconductivity.
Even the linearized approximation, it's hard to analyze this?
Yes. It's a non-trivial analysis for this linearized approximation. And of course, there's also numerical analysis beyond this linearized approximation, which is even more difficult. But people did this, and strange. Well, there are some controversial results there which are still not clarified, because there are some claims that even this thing is unstable, but I don't know. Anyway, so that's just shows you how. So we're discussing physics of early 20th century, and suddenly it's one step, and we are in the unknown, where we get some controversial results and so on. It's very, very close to physics is. By small deformation, you can get very easily. Some correct results are unstable under small deformation. Put it this way. Anyway, let me tell you one more beautiful thing about vortices. As I said, it's mostly important for quantized vortices, and quantized vortices have been observed quite explicitly in many systems. It's quite beautiful and wonderful. The loss of when you exceed some velocity, you get loss. You lose superfluidity if you have a capillary and you have velocity is too large. Turns out that you generate. There's an instability in which the flow generates vortices, but three-dimensional vortices. And let me now say a few things about three-dimensional vortices, and we will go to other creatures. To generalize it to three dimensions, vorticity is, we have the general formula in any dimensions. And actually in 3D you can write it down in this way, where once again the epsilon tensor is epsilon 1, 2, 3 is 1, and then if permutation is even, it's 1. If it is odd, it's minus 1. So it's totally antisymmetric numerical tensor, and you can show, well, we discussed many times already, that omega transforms as a vector under rotations. And you see immediately from here that we can invert it. And the divergence is identically 0. As we already discussed, it's very similar to the magnetic field expressed in terms of vector potential. The divergence of magnetic field is 0. And now we have to decide. Let's suppose that we concentrate vorticity. In 2 dimensions, we concentrated it at a point. In 3 dimensions, actually we have to concentrate it on a line. And those lines must be closed or go to infinity in order to satisfy this equation. Let me explain this. If we have a line of vorticity, we can write it down in the following way. Suppose we have a contour, and we integrate over ds. We write down dx alpha over ds. And we take the delta function of x minus x of s. Let's look for the solution in this form. This is actually, let's say you parameterize it from 0 to 1. It is obvious immediately that if you take the divergence of this guy, you get integral ds from 0 to 1, dx alpha over ds, delta d alpha, delta of x minus x of s. And this is the integral ds, dds of delta of x minus x of s. And it will be 0 for the closed contours. So that's just the formula. So for that we need x at 1 equal to x at 0. If they are not equal, then we have a problem. We violate this relation. And this relation more or less follows from the definition. So instead of point-like vortices, we now have smoke rings. Actually, smoke rings are just those lines of vorticity. But this, in the case of the two-dimensional case, I'm doing it. In two-dimensional case, single vortex was not moving. It was sitting at, so it was given by this formula. In two-dimensional case, in three-dimensional case, excuse me. So let me write it down once again. vorticity is concentrated on a line x of s, and this line must depend on time, because even if you take, for example, a two-dimensional section, what you will see are two static vortices, and they attract, obviously cannot stay at rest. So you have an equation. The smoke rings are always dynamical. You have the function x of s and t, and now try to guess what kind of, it satisfies the equation. You can write down the analog of this equation for the function x of s and t. So I would write x dot of s and t equal to something. And it could be derived, the equation could be derived from this relation, or the three-dimensional analog of this relation. But it can also be guessed, conjectured in the same way we conjecture two-dimensional equation. Well, so what should be the idea? How to, when you have a, try to remember when we had two dimensions, how we derived the motion of a single vortex. What did we do? What did we say? Where all these equations come from? Yes?
So we just looked at the effect of neighboring vortices at that point?
Yeah, we basically said that this particular vortex moves in the field created by all others. And this one by all others, and so on. So all we have to do now is to find the velocity induced by all others. And that will be the analog of this equation. How to find this velocity? That we will probably... Well, it's not difficult at all. We have the relation that this should be equal to epsilon alpha beta gamma d beta v gamma. And I will not go, I think it's too late already to, it takes some calculations. What we will do, we will solve this equation, which is rather trivial. It's just the typical problem of magnetostatics. Omega is very much like the line of magnetic force. So it's just a standard equation which is easy to solve, and then we will find we will write down this equation, which says that the velocity of a given piece, that it moves in the velocity fields created by all other pieces of this vortex line. And it's not difficult to write, and we will do it next time. It's very difficult to solve. But that's the last comment. We will see some fantastically beautiful things about those smoke rings, which impressed Kelvin and Helmholtz so much that they thought that the whole world consists of that atoms consist of the lines like that. The fantastic property was that if you have a linking between two vortex lines, we will see it next time, they will remain linked forever. And the different type of knots there's topological symmetry which preserved various type of knots. And that, as I said, was string theory in 19th century. People try to. So it's a nice subject, but I should stop here really, because it will take some time to derive all this.